All right, so we are going to be reviewing Texas TEK 8.6c, Newton's laws, which is to investigate and describe applications of Newton's law of inertia, the law of force and acceleration, and the law of action and reaction, such as in vehicle restraint, sports activities, amusement park rides, Earth's tectonic plates, and rocket launches. Let's dive in. So we got Mr. Newton here, responsible for lots of things. You can click the video for a TED Ed, but it's got some great stats there. Really influential guy, and we named end up naming the laws, the Newton's laws of motion after him, for discovering how this motion works on planet Earth. So Newton's first law is the law of motion, which is an object at rest tends to stay at rest, or an object in motion tends to stay in motion until an unbalanced force acts upon it. Simply meaning that an object will continue doing what it's doing until until an unbalanced force acts upon that object. So in this case, as you can see in the picture here, you have the card and the coin in the cup. If you flick the card fast enough that the friction doesn't affect the coin that much, the card will move and the coin will fall into the cup. Great example of inertia. Another great example of inertia is just sitting still in your chair and not moving. That's an object at rest. So, this object it says describe it, look at the coin will not move if the card is flicked fast enough, meaning the object will stay at rest. So, in other words, an object will keep doing whatever it's doing until it's acted on by another force. So a couple little things that you can click on and check out. So inertia, great vocabulary word, is an object's tendency to resist a change in itself. And the greater an object's mass, the greater the inertia, right? Like a big truck and a small car. The greater the mass, the greater inertia. The greater the object will resist its change. A big old boulder versus a small rock. The small rock won't resist it as much as the big boulder. The greater an object's mass, the greater its inertia, and the larger force needed to overcome the inertia. So which vehicle would take longer to stop if they were traveling at the same speed? That would be the truck, of course. Think of 18-wheelers on the highway and the small little car. The small little car can go in and out and back and forth quickly, whereas the truck cannot. So you have that. Now let's talk about car restraint or vehicle restraints. When a car is going 80 kilometers per hour and is stopped by a brick wall, your body keeps moving at 80 miles an hour. So in this case, you would see that the person would keep going if you are not wearing a seatbelt. So Newton's first law is a great example of not wearing a seatbelt. The individual will keep moving after the car stops. Kind of like if you're on a skateboard and you're riding your skateboard and you hit a curb, you will keep moving and your skateboard will stop. So great example of Newton's first law. So now let's talk about Newton's second law. It's force equals mass times acceleration. The acceleration of an object depends on the mass and the magnitude of the force acting upon it. I call this the sports law. Like the hockey players here. The hockey players carry a mass and they're moving at a speed and they can apply a force to another player, right? Their mass is their body, how much they weigh with the stuff that they're carrying. And their acceleration is how fast they're moving and the force that they strike the other player. Also think about if you have a 10-pound bowling ball and you're holding it up high and then you drop it. Well, you got to know what the acceleration, if you want to figure out what the force is that it hits the ground, you have to know the acceleration of that drop, which in this case would be the pull of gravity on planet Earth, which is 9.8 meters per second squared. So we like to round up in middle school, so 9.8, we round to 10. So 10 times 10 would be a Newton's force of 100. So 100 newtons striking the ground. You can actually calculate that force. F equals ma. If you have the mass of 10 kilograms times the acceleration of 9.8, which we round to 10, 10 times 10, force of 100 newtons. And you can also use this like a triangle. So if you're considering the triangle like so, you're just kind of following my mouse, know that the force would be up top and M and A would be below it. And so you could use the force triangle just like the speed triangle. How much more force is needed to push the car on the right with the same acceleration? So we're trying to figure out force. So you need to multiply the mass and the acceleration, and then you would know how much force would need to push the car, or how much force would be needed to push the heavier Volkswagen bus. The greater the mass, the greater the force needed for the same acceleration. What happens if two cars with different masses travel at the same speed down a hill towards a stop sign? The car with the larger mass will require more force to stop, just like the truck and the small car that I talked about earlier. If you were to apply the same brake force to the big truck and the small car would stop much faster than the truck. The truck takes a while to stop. Now we'll move on to the third law of motion, which is action-reaction. For every action, there's an equal and opposite reaction. So we have an athlete pushing the bar upwards, and the bar pushes the athlete downwards. You can actually feel the force of the bar pushing down on you when you go to lift it. And the bowling pin pushing the pins to the right, and the pin pushing the bowling ball to the left. You can see that if you've ever been bowling before. You can see what happens to the bowling ball once it strikes the pins. Now you can throw a bowling ball with great enough force to where it doesn't look like it's changing the trajectory of that ball very well, but if you roll it slower, you can most definitely see the pins changing the direction of the ball. So we like to call this the rocket law, the third law. The rocket taking off from Earth is a great example of Newton's third law. The action is the engine and the gases firing downwards, and the reaction is the rocket and spaceship going upwards. Also, recoil of a gun, firing a handgun at a range to hit a target. The bullet goes forward and the gun recoils and goes backwards. A couple of great examples of Newton's third law. And this is a good instruction of how the rocket works in the third law. So just to go back to make sure we covered it, amusement park rides, lots of great examples of all three Newton's laws when you're talking about riding the Titan. You know, you have an object, you have inertia, an object changing going from stop, not moving to moving. And then you have the force at which there's a movement. You have your mass and your acceleration of the car. And then you have action, reaction, whereas your, actually when it goes forward, you move backwards. And then when it comes to a quick stop, you kind of move forward, but the restraints that you have pull you back. And that's the last example that I'll give is, when I first said that not wearing a seatbelt is example of Newton's first law, because the object will stay in motion, the person will stay in motion until something acts upon that person, whether it's the tree or the pavement or something after the person is ejected from the car, versus wearing your seatbelt is a great example of third law. The action is the individual's going forward. The reaction is the seatbelt throws them back in their seat. So those are your explanations of Newton's 3 laws. Good luck on the upcoming work. Thanks, guys.